Hello, welcome to video number 2 in the Zero to Hero series. I am Mr. Holmes. Alright, so without further ado, let's get into what is computer memory. Alright, computer memory is also known as primary memory. It is also called RAM, stands for random access memory. It's volatile, meaning when it loses power, the memory content is also lost. And the purpose of RAM, remember, is to service the CPU. How so? Well, the CPU's job is to fetch, decode, and execute instructions which are going to sit where? In primary memory. So we need a relatively fast, and relatively as large as we can get it, memory store to store all the data and all the instructions the CPU is currently running. So, over time, the technology that's been used for primary memory has been something known as a DRAM, or dynamic RAM. Dynamic RAM is built from a very simple circuit. It's built from one transistor and one capacitor. Capacitors, if you've studied them in science, store charge. However, they don't store charge for very long. Over time, the charge leaks away from the capacitor, and so for the memory cell to retain its content, it has to be continually refreshed. During a refresh cycle, this RAM cannot be accessed by the CPU. This slows things down a lot, and this is known as a bottleneck. So that is the disadvantage of using DRAM for main memory storage. There are a number of advantages to it, however. It's relatively cheap, and because the circuits are so simple, a great number of them can be fitted into a really small surface area. So we say it has a high density, which in turn means that we can create storage areas of gigabytes relatively easy and relatively inexpensively. This may seem all fine and dandy, but you need to understand something called latency. Latency is the amount of time that a component within the system takes to respond to a request by another component. So for example, the amount of time that RAM would take to respond to a request by the CPU for it to be read or written to is quite significantly high by comparison. As you can see from this chart, RAM has a latency of about 100 nanoseconds compared to the CPU and its registers, which responds in about 1 nanosecond. So the CPU is typically running about 100 times faster than RAM. This means that a tremendous amount of time that the CPU has at its disposal is lost or wasted waiting for DRAM's refresh cycles. To try and speed up the system as a whole, another type of memory has been created called SRAM. SRAM is built from 6 transistors. Now, unlike DRAM, SRAM, because it's built on electronics and transistors, as long as it remains powered, the memory cell will retain its contents without the need for refresh cycles. No refresh cycles needed here. But because it's built from 6 transistors, these take up a lot more surface area. So the density of the circuit in the dies is much lower, meaning we can fit a lot less in the same amount of surface area. Consequently, not only this makes SRAM a lot more expensive, but also means the capacity of it is a lot lower than that of DRAM. Capacity is in the order of kilobytes or megabytes. So because the sizes are extremely limited, it's not appropriate for us to use static RAM as the main primary memory store. Instead, a solution has come about whereby we store only the most relevant and commonly needed, most recently needed instructions or data in this much smaller but much faster static RAM, known as cache memory. Cache memory has a latency of about 10 nanoseconds. So that is, in other words, it's 10 times faster than standard RAM, which means the CPU can spend a lot more of its time executing instructions and data that it already has access to without the need to having to go back to much slower dynamic RAM main memory. It's important to note that both DRAM and SRAM are both types of RAM. They are volatile. RAM is considered to be volatile, meaning no power, no memory. Both DRAM and SRAM will lose their memory contents if not powered. To this end, this means that both SRAM and DRAM have two huge problems. The first one I've just talked about is that the DRAM and SRAM are both, RAM in other words, is volatile. No electricity, no power. The issue of RAM's volatility and its limited storage capacity is not a new one. It is one that has been around for as long as computers have been in existence. Let's first of all address and understand why RAM being volatile is potentially an issue. Upon booting, the computer's memory is empty. What we need is some means in which the CPU can pick up instructions to run even though the contents of primary memory have been erased. So what we need is a new type of memory that not only can store instructions and data, but is electronic and can retain its contents even when power has been lost. This type of memory is known as ROM memory. RAM is volatile. It's designed to be fast and directly accessible by the CPU. ROM, on the other hand, is not really built for speed, but it is built for going the distance. It's built for retaining instructions or data in the absence of power. This is done through making use of a similar but different technology to what RAM is constructed from. Both RAM and ROMs are electronic, so it means they store bit patterns as electric voltages being high or low. ROMs are built on a type of technology known as an FGMOS, or floating gate metal oxide semiconductor. This type of electronic technology can retain the memory values that have been written to it even in the absence of electric power. So we say that ROM is non-volatile. The typical applications of ROMs are for BIOSes, basic input-output systems, and firmware, which are programs burnt onto an actual ROM chip that the CPU will execute. We now turn our attention to solving RAM's second problem, namely that of its limited capacity. Virtual memory is using secondary storage as if it was primary storage. It pretends to be primary storage. So for instance, a memory block in physical memory, block C, is no longer at this point required. It is written to the swap file, and the required block A is read from the swap file on secondary storage and reloaded back into RAM. This gives the system the appearance that it has more physical memory than it in fact actually does have. This very clever trick, however, comes at a tremendous cost to system performance. To understand this, you need to understand what we mean by latency. Latency is how long a component within the system takes to respond to a request by another component. For example, how long does RAM take to respond to a request by the CPU? RAM has a latency of about 100 nanoseconds. So CPU to RAM to cache to RAM is a factor of 10 each. This factoring does not continue when we move from RAM to secondary storage. Hard disks, on the other hand, have a latency of about 10 milliseconds. A millisecond is only 1,000th of a second, so there's a factor of nearly 100,000 in speed difference. To put this in a context that you can understand, is if the CPU speed of 1 nanosecond was equated to a single second, then cache memory would be accessible in a matter of seconds, whereas primary RAM would be accessible in minutes. Disk memory would actually equivalently be accessible in decades by comparison. So the noise, the disk thrashing you hear when your system makes use of virtual memory is not a good sign. It is a sign that you've run out of RAM and the system performance will drop significantly because it is waiting for decades by comparison for the required data and instructions to be swapped from the swap file back to primary memory. And this concludes our discussion on memory. Thanks for watching.